So welcome for the another beautiful presentation on network analysis. Just we have started with our previous presentation on this network analysis. There we have seen the basic primary elements that are being used in any electrical networks. Those are resistance and capacitance and then inductance. Basically, those are identified with the letter resistance or inductance is L actually, and then capacitance is C in general, right? These are what we have seen, and the physical representation of the resistor is something like this. This is the representation of resistance R actually, and similarly if you see the inductance, that is denoted by simply it is the coil. If you take a small copper wire and if you can, right, so make in such a way that in terms of okay, so this is simply a coil actually. This is what the inductance, whereas the capacitance is something like this. It is something like this. This is the capacitance. These are the primary basic electrical elements: resistance, inductance and then capacitance, right? So we are discussing about the resistance actually. In our previous presentation we have seen the various connection with respect to the resistance, how the resistances can be connected, that we have seen. So basically, in fact, if you consider these three elements, maybe resistance or inductance or capacitance, whatever it is, they can be connected either in series connection as well as parallel connection, right? So as per the requirement of the circuit or as per the requirement of the application, we can connect these as per the requirement. Can be connected in series, can be connected in parallel, no problem at all, right? So in this connection, we have seen in our previous presentation the series connection of resistor we have seen. In today's presentation, let us see a brief simple information about the parallel connection of the resistance. So I will explain you that the parallel connection, right? So it is parallel connection, parallel connection of resistance means say for example, you can take either 2 or 3 whatever it is. So whenever we are discussing about the combination or the connection, so the required resistance must be more than one. So with one resistance we cannot have any connection now. That is why we must need more than one, maybe two, maybe three, maybe four, or whatever it is. So say for example in parallel connection, how the connection looks like. Let us say for example I have two resistors. Let us say this is one resistor, I am calling it as R1, and I have one more resistor R2. This is something R2, and in any given circuit, let us say these two are connected like this. These two resistors are connected like this, and these two are connected across certain voltage source. I have given some DC voltage here. This is voltage plus and then minus, already I have indicated here. Therefore, right, this is the VDC. Let us say VDC, DC voltage, right? So therefore, now if you connect the resistances means R1 and then R2 in this connection as the fashion which I have shown, then these two resistors are said to be, they are in parallel to each other, right? So for example, I am explaining with two resistors, then you can add one more resistor also, R3, R4, R5, or any number of resistance you can add, no problem, but the concept remains the same. Therefore, let us carefully listen here. So whenever these two connectors are connected in this fashion across certain voltage, then obviously these two are called they are in parallel connection, right? So what will happen then actually in this connection? So whenever we use the DC voltage here, then obviously certain amount of current flows through I. I is the current. Because of this voltage source, some amount of current will be generated, and that current I will flows through the circuit actually. This is a simple circuit, or this is a simple network you can call. Nothing wrong in that. You can call it as a circuit, or you can call it as a network. Now we are analyzing this particular circuit. Okay, so this is with the help of this VDC. Let us imagine that the current I is flowing from here to it flows in this direction as I have shown with the arrow mark. Clearly see that now here at this you can call it as some node, because at this node, let us say I will so let us mark that as node like this, right? Therefore from the here node you can write like this is R1, and you can represent like this also R2. That is the meaning of. So this is R1, this is R2, both are grounded here. So means a negative potential. This is given to the negative potential. This is plus, this portion is at, I mean this point is this end. Both these ends are tied together, and that is given to the plus sign of the voltage. This is the minus sign actually. Ground is nothing but obviously minus sign. Remember that. Therefore, this is the point actually. This is the point. Here, this is, I can call it as some node point, right? I can call it as some node point or nodal point, whatever it is. So, once the current I starts from here and it goes to this nodal point, at this node point, this current will be distributed. The current I will be distributed with respect to both R1 as well as R2. How it can be distributed? So this I goes to up to nodal point as I, and from here, so this can be I1, and from through this R2 it goes as I2. Understood? So up to this nodal point, the current I flows up to the nodal point. At this particular nodal point, it will be distributed according to the resistances. So here we have two resistance. Therefore, in one resistor, let us call as I1, and in another resistor, that is I2. Means that what actually at this node if you see, so this is entering current. This I, whatever is going towards this node, you can call it as entering current. From this node, it is distributed like I1 and again as I2, is it not? So, it is splitting, otherwise the current I is splitting into two branches, because R1 is one branch, R2 is another branch. Therefore, in R1, it is splitting as I1, in R2, it is splitting as I2. Therefore, now according to your KCL, what is KCL? Kirchhoff's current law. Kirchhoff's current law. What this law states that according to this KCL or Kirchhoff current law, the sum of entering current at particular node is equal to the sum of leaving current. Is it not? The sum of entering current is equal to the sum of leaving current. That is what Kirchhoff current law, that is one of the very, very important law. Widely it can be used in analyzing the electrical circuits. Therefore, according to your Kirchhoff current law, I is equal to I1 plus I2. That is the very, very important relation we have to remember as far as this circuit is concerned. So, I is the entering current. Sum of the entering current. Sum of is nothing but how many currents are entering here? Only one current, I only. Therefore, if you sum it, only I will be there. Therefore, I is equal to sum of leaving current. Sum of leaving current means how many currents are there? I1 and I2. If you sum those two, I1 plus I2. Therefore, entering current is I is equal to leaving current from that node I1 plus I2. This is what your KCL. Means that what you know, there is a one important point to note down in the parallel connection also. Right? I will explain you carefully. Listen. Now, by simply seeing this particular circuit, one can easily identify that So the current in the first branch, or the branch, I am calling it as the first branch, means the resistance R1. This branch I am calling as first branch, and the resistance R2. This particular I am calling it as second branch. So in first branch, current I1 is flowing. In the second branch, the I2 is flowing. Means that what you know, whenever the resistors are parallel, different current flows. It's not same current like in the case of series connection, which we have seen in our previous presentation. In earlier presentation, if you recall in previous presentation, under our network analysis subject, there I have explained you that whenever the resistances are connected in series, a same current flows through both the resistances or all the resistances which are there in the series. In previous presentation, we have connected two resistors R1 and R2. Then, so the same current I is flowing through R1 as well as R2. So, in the series connection, same amount of current flows. Whereas, in parallel connection, it is not same. It is definitely different. It is definitely different current flows through like this. So, in the R1 branch, in this branch, current I1. In the second branch, the current I2. Obviously, I1 is not equal to I2. Sometimes maybe equal, no problem, but it is not same. Both are different. That is why I have indicated them as I1 and I2. And in fact, if you add these two, that must be equal to the input current, means the entering current I. Clear? Good. Now means that what? The first point is that, so in the parallel connection, the current will be different. Different current flows through different branches of the resistances. That is the first point. And another point to note down here is that, very, very important point, whenever this kind of electrical network is given to you, and you are asking to find out what is the voltage drop across this resistor, what is the voltage drop across this resistor, voltage drop, let us call it is R1. No, let us assume that I am calling it as something V1. Let us say V1, V1 is the voltage drop across R1, right? And similarly across this R2, let us imagine that V2 is the voltage. Let us say, for example, okay, V1 is the voltage drop across R1 and V2 is the voltage drop across V2, right? So, how these two branches are there? And both are in parallel, For this parallel, what is the input? DC voltage is your input voltage. Remember that whenever the resistors are connected in parallel, your V1 is equal to V2 is equal to VDC. Very, very, very important formula to remember. Means that what you know, in the parallel connection, the same amount of voltage, whatever the voltage you gives here as input, the same voltage will comes across this resistance, the same will appears across this resistor also. Clear? So that is very, very important to note down. Therefore, the voltage remains the same in parallel connection. The voltage across each resistor remains the same, whereas the current flows through the resistor is different. That is the point here to learn today in today's presentation, right? So the voltage remains the same across each parallel combination of the resistor. The voltage remains the same across each resistor, but the current flowing through each resistor is different. That is what that is denoted, or that can be represented like this. Clear? So this is very simple example that I would like to explain in today's presentation, and I hope that you have understood well. This is what the parallel, and moreover another important thing is that, just what is the equivalent resistor? What is the equivalent resistor in parallel combination? That is very important also. In fact, let us see what is the equivalent resistance. Equivalent. What is the equivalent resistance under this parallel combination? So equivalent resistance is denoted by R suffix EQ, R equivalent. So to determine the R equivalent for this parallel combination, it can be represented as, let us see, 1 by R equivalent is equal to 1 by R1 plus 1 by R2. That is the expression we have to consider. So in parallel combination, the equivalent resistance or the total resistance can be determined by using this formula. 1 by R equivalent, we have to write like this. 1 by R equivalent, because in parallel combination, no, that's why we have to write like this. 1 by R equivalent is equal to 1 by R1 plus 1 by R2. This is R2. Okay. Or otherwise, if you have some R3, R4, R5, R6 and so on, so then you write 1 by R3 plus 1 by R4 plus 1 by R5 like that. So for these two resistors, as we have two resistors in this circuit, this is the simple expression. And if you can simplify that further, and I can give you that expression as the equivalent resistance can be written as like this. So 1 by R equivalent is equal to 1 by R equivalent is equal to, take the LCM, you can write R1 into R2 by, this is R1 plus R2. You can write like that. So now I need to find out R equivalent. Just you just reverse this expression, then you will get R equivalent. R equivalent is equal to what? It is simply R1 R2 by R1 plus R2. This is what your equivalent resistance for two resistor. This is what the R equivalent. This is the equivalent resistance. This is the equivalent resistance for a parallel combination of R1 with R2. Right? I hope you understood well, and let us finish off this presentation here, and we'll continue with some more simple examples to understand the basic concept of this network analysis in our subsequent presentations. Right? So I request you all that if you are understood this very well, and share your observations and comments, and I think, and you share this information with your friends also, and yeah, your feedbacks and comments can be highly appreciated and can be considered to improve the content of in our subsequent presentations. Right? So thanks for watching this video, and we'll meet in the next subsequent presentation. Till then, have a wonderful day.